Good morning, friends. In the last lectures, we completed bending stress chapters. So that's why today I am starting new chapters. Is the above the fourth unit, that is shearing stresses. So as you know, on the beam, shear stress is induced and simultaneously bending stress also induced. And the effect above the bending stress, that is more as compared to the effect above the shear force. So that's why generally we consider bending stresses in the design above the beam, but the effect above the shearing stress, that is also is not to be neglected. So that's why for designing above the beams, effect above the shear force, that is also is to be considered. So that's why we are studying the shearing stress above the chapter. Suppose consider this is a small length above a beam having UDL W and this is small cross section A, B, and this is C, D, having depth D and length equal to dx. Its area of cross section. So this width equal to, this is B is its width, this is EF, so the moment and this is section, this is distance y. Here you consider this is, and this is A, B, and this is CD, and this distance equal to dx, length equal to dx. So consider a small portion A, B, C, D up a beam having length dx, depth D. So D is the depth and width B. So this width equal to B. So that's why here's at every sections shear force is acting and bending moment is also that vary. Now suppose at AB sections this is moment occurs is the M, and across CD sections, so this moment is the M plus delta M. So that's why let M is bending moment at AB and M plus delta M bending moment at CD. So F shear force at AB and F plus delta F shear force at CD. I is the moment of inertia of section about the neutral axis. So that's why here's moment of inertia equal to, because this is B and depth equal to, so this is D. So total moment of inertia equal to, this is total moment of inertia equal to BD cube divided by 12. Now consider a elementary strip EF. So this is EF. So this is not AB. So this is EF. So because this is front view and this is side view. Elementary strip at a distance y from the neutral axis as shown in figure. Now let this is intensity of bending stress across AB at a distance of y from neutral axis, and A is the small a, area of cross section of strip. We know that sigma divided by y equal to m divided by I. So that's why sigma equal to m into y divided by I. Y is the distance above the extreme fibers. Suppose this is first equation. Similarly, this is sigma y equal to m plus delta m into y divided by I. This is second equation. So this delta, this is intensity, delta plus delta y, intensity of bending stress across CD at a distance y from again neutral axis. So that's why force acting across AB equal to force acting across AB equal to force is nothing but stress multiplied by area. So that's why here also we can consider so that's why here stress equal to M into Y divided by I into A. Suppose this is third equation. Similarly, force acting across CD equal to M plus delta M divided by I into Y into area of cross section, and this is suppose fourth equation. Therefore, net unbalanced force on the beam equal to M plus delta M divided by I into YA minus M Y into A. So here's this M and that will get cancelled, and dm into I multiplied by YA. This is area of cross sections for small area. So that's why the total unbalanced force, so this is small area, total unbalanced force acting above neutral axis found out by integrating above equation between 0 to actually this is d by 2 because this distance is important. So that's why F equal to Y equal to 0 YC delta M divided by I multiplied by YA into delta Y. So this is delta M is this is dm divided by I multiplied by this is A into Y bar. Otherwise, for understanding purpose, 0 to d by 2 AY into dy, and this is F equal to dm, this is capital A into Y bar. So where Y bar is the distance, centroidal distance above the section above the neutral axis. So here please understand what is mean above the y bar. So A is the area of the beam above neutral axis, and y bar is the distance between center of gravity of the area above neutral area and the neutral axis. So this is clear. So this is equal to F equal to so this is right. So this is dm divided by y or I divided by A into y bar. All right. Now shear stress equal to total force divided by area. Now total force equal to, so please understand this, total force equal to dm divided by I into A y bar. Area equal to this dx multiplied by b. Dx multiplied by b. So this is dm divided by dx multiplied by A into y bar divided by, and this is nothing but S A y bar divided by, and this is I or BI. So this is important relation. Shear stress equal to, where S is the shear force, S is shear force and tau is the shear stress. Now you know so that what is meaning above the tau. So next we will see shear stress distributions for beam sections of various shape. So next articles. shear stress distributions, shear stress distribution for beam section of various shapes. So shape may be rectangular sections, shape may be circular sections, shape may be hollow circular sections, hollow rectangular sections, T sections, I sections. So for that's why we study theoretical shear stress distributions for rectangular sections. Means first we'll see for a rectangular section. So for rectangular section, consider this is a rectangular section. This is AB, CD, and this is EF. And positions of the neutral axis. This is neutral axis. This is, and this is Y, and D is depth, and width equal to, this is B. So that's why consider level EF. So this is very important, EF at a distance of Y from, so this is neutral axis. The intensity of shear force, or the intensity of shear stress at these sections equal to tau equal to formula SAY bar divided by now BI. So where AY bar is the moment of the area above EF shown shaded about neutral axis. So this AY bar is the moment of the area, means this is the moment above the area, EF shown about the neutral axis. So that's why AY bar equal to so area equal to B into, now this distance is the total D by 2, and this is D by 2 minus Y. d by 2 minus y. So that's why d by 2 minus y multiplied by, now this is y bar. So y bar equal to, this is total average, means this is d by 2 plus y equal to d by 2 plus y and divided by 2, right? So ay bar equal to, you can write this is b by 2 d2 square divided by 4 minus y square, right? So tau equal to, now by putting, suppose this is equation first, so by putting value of ay bar in equation first, so that's why tau equal to b by 2 4 multiplied by, this is s divided by b into I. So this b will get cancelled, and tau equal to s into d square by 4 y square divided by, this is 2I, because this 2 and this is I. Now at the top edge AB, y equal to d by 2, and about neutral axis y equal to, so this y equal to 0. So we are considering this total area. This total area. So that's why now shear stress top, at the top, this is equal to y equal to d by 2 so that's why for d by 2 square divided by 2I, so top equal to, this become 0, because d square divided by 4 minus d square by, and about neutral axis because here y equal to d by 2 and here's y equal to 0, so this is 0 square divided by 2I, so that's why this is yes d square divided by 8I, or neutral axis, S into d square 8 into I equal to BD cube divided by 12. I equal to BD cube divided by 12. This is for rectangular sections. So that's why this is equal to 3 by 2. So this will get cancelled. S divided by BD. Or this is nothing but this is S by BD. This is average shear stress. This is average shear stress. So this is important relation. Or this maximum equal to 3 by 2 average shear stress. So that's why here distributions above the shear stress diagram at the top edge this is 0, bottom edge 0, and this is, so here 3 by 2 into S divided by BD, and this is tau max. This is for a rectangular section. So that's why today I will take one problems related with the so after that the different sections means that circular sections and I sections we will see in the next class. So please note down. A timber beam is simply supported at the ends carries a concentrated load at midspan the maximum longitudinal stress is at the maximum shearing stress is tau. Find the ratio of span to the depth of the beam. Ignoring the self weight of the beam. If stress equal to, so this is allowable stress, and shear stress equal to 1 Newton per mm square. Suppose this is a beam, load acting W, length equal to, let this is L, cross section BD. This is A point, B point, and this is C. This distance equal to L by 2, L by 2. So that's why moment equal to what is relation here? Otherwise force equal to shear force at A and B support equal to S equal to, this is maximum W by 2, S equal to. Similarly, maximum moment of resistance, you can call as a resistance, M equal to WL by 4. Why this is WL by 4? Because about C, and this is W by 2 and this is L by 2. So because this is force multiplied by this distance, this is WL by 4. Now, as we knows, M divided by I equal to sigma B divided by Y. So that's why sigma B equal to M divided by I into Y. I equal to BD cube divided by 12. So that's why sigma B equal to M equal to W into L divided by 4 divided by I, and Y equal to D by 2. So this is right. Anything I am missing? All right. So WLD divided by 8I or sigma B equal to WALD 8I so this is equal to 3/2 this one BD square that is correct sigma and tau equal to 3/2 into average shear stress. S divided by BD. Suppose this is first equation and this is second equation. So here tau equal to 3/2, shear force equal to, so this is W/2. Since S equal to, this is the maximum shear force. So tau equal to 3W divided by 8 BD. Oh sorry, this is 4 BD. Alright, suppose this is second equation. Now, equation first divide by equation second. Sigma B divided by tau 3/2 W into L BD square multiplied by. So this is 3W at the bottom and this is 4BD. So what will get cancelled? This W will get cancelled, B will get cancelled, D square and this 1D will get cancelled. This 3 get cancelled and sigma B equal to divided by tau equal to, this is 2L divided by D. Or L by D equal to sigma B divided by 2 tau. So that's why sigma B equal to, this is 12 and this is 1 given. So L by D equal to, this is 6. What is asked? A ratio of span to depth. Span to depth, that is correct. Find the ratio of the span to depth, means this is your expected answer. So I think you understand these problems. So due to, because this is today's first lectures, that is on the shearing stress, so that's why today I stop here, and remaining portions about the shearing stress I will cover within 4-5 class. So after that we can start, that is the 5th units. So that's why today I stop here, and we will continue remaining portions about the shearing stress in the next class. Thank you.